This recording is for Primary Math 5. We're working in the Intensive Practice book on pages 12 through 17, the word problems assigned for this week. Number 1 starts out with some basic problems. Josh saves 75 cents a day out of his allowance, and he does that for a month, which they define as 30 days. And so if he does that every day for a month, we're just doing a simple multiplication problem. We end up with 2,250. Keep in mind that's cents, so we could change that to $22.50. Don't stop there. The question says at the bottom, give your answer to the nearest dollars. So our final answer is $23. Certainly you could change this to cents earlier, but then you'd be multiplying with decimals, and I'm all about doing it the easy way and transferring it once you've got the math done. Number 2, a man buys a living room furniture set. He paid a deposit and he had a balance of $1,499. And he pays that by monthly installments. You might need to explain to your children what an installment is, that a monthly installment means you're paying it for a year. Every month for a year you pay it. So we're going to pay that amount over the next 12 months. And it tells us to estimate the amount of money that he paid each month. The estimate of this question is, how do you estimate that? In some respects, estimating it, never sure what they mean to do that. Okay, if you take it up to 1,500, it's a more even division, and in fact it comes out exactly evenly. So if you do that, then it happens to work out. It's just an easier number to deal with anyway, so maybe that's what they mean by estimate. It does give us the right answer. When I do the division, I'm going to pause and make a couple pictures for you. I want to make sure you understand what I'm doing when I do the division this way. It's the same thing as what we'll call the algorithm, the steps of division that we learned, and it's certainly fine to do both. I like for students to see this division on the left side of the page because it helps it to make sense. What we're basically saying is, if I take 1,500 and call it 1,200 and 300, then 12 hundreds divided by 12 is 100. And that's where this 100 comes from on that other side. And notice when I do that, what I have left is the 300, which in effect is what I have here. And when they say I have 2 tens, that's because my 24 tens divided into groups of 12 gives me 2 tens left. And then I complete the problem by finding that after I take those 2 tens out, I have 60 left. And when I have 60 divided by 12, that ends up with 5. So both of these show 125. I think the one on the left page makes a lot of sense. Even if they do it on the right page, even if they do long division like that most of the time, every once in a while do it on the left side like that and make sure they understand how to do division and what it means to divide. But the answer to this problem, the back of the book gives it this way as well, is $125. So really the only estimation skill that I used was to change the $1,499 into 1,500, just because it doesn't give you so much of a messy number, and it turns out to work out evenly, although you wouldn't really know that starting out. Number 3, we have a bottle that can hold 450 milliliters of milk. There's the best milk bottle I can draw for you. It can hold 450 milliliters, and we have 8.8 liters of milk to go into that. And the question is, how many bottles do we need? Now, the first thing that you and your students should think about when you're solving this is the realization that, what are we going to do with the remainder? Okay, we're going to totally fill up some bottles, and then we'll have a bottle that's whatever is left in the bottom of it. You know, the last bottle is not going to be full, most likely, right? So we're not going to say 15 with the remainder of, 15 bottles with the remainder of 10 milliliters. That would mean 16 bottles, right? So the remainder is going to go up to another bottle. Okay, and so this would be an integer theory. We talk about things that would have to go up to the next integer, and even if it's a small amount, even if you just have 1 milliliter left over, you've got to have another bottle, because the question is, how many bottles are required to hold that milk? You can't leave it anywhere else. It has to all go into a bottle somewhere. So one thing that I would do to make this problem solvable is to go into units. Of course, you have liters and milliliters. I'm going to make them both into milliliters so that I can do this, do the division. And I'm going to say I have 8,800 milliliters divided by 450 milliliters. When I look at this, what's screaming out at me is the fact that 450 times 245s is 90, so times 20 gives me 90 with 2 zeros. Remember how we do the zeros there? These 2 zeros carry down here, and 45 times 2 is 90. That's a mental math way of doing that. So what I know is that it takes 20 bottles to hold 9,000 milliliters. Now, if I have 20 bottles, the capacity that I could hold is 9,000. All I need is 8,800. So my last bottle will have room in the top. But without really doing the bottles, because they gave us an easy problem, we can see that it's going to take 20 bottles. And again, that last bottle, let's draw the last bottle a little bit different. The last bottle could hold 450. It's only going to be about half full. It's going to have, actually it'll have 250. What it will miss, there'll be 200 milliliters at the top that it could hold, because we could hold as much as 9,000. I only have 8,800. So the 200 at the top is not going to be full. But the question that it asks me is, how many bottles are required? Now, when they give you easy numbers, it's okay to do it the easy way. And in this case, because I noticed the 9,000 was so close, I didn't do the harder part of the math. If I did, I could take 8,800 and divide it by 450. I could do that with long division. I could even take that and say, well, that's 880 divided by 45, and I would get 19 with a remainder of 250 or 200, I guess, 25 if I did it this way. And what I'd have to realize is that 19 bottles, but I have some left over, so that would mean 20 bottles. Okay, this problem would give me 19 with a remainder of 250. If I dropped the zeros, I'd get 19 with a remainder of 25. Either way, you have to realize that you've got to go up a bottle in order to hold all of the milk. Problem number 4. A coat costs $105 and it's 3 times as much as a sweater. Find the cost of 3 coats and 5 sweaters. If I take this and divide it by 3, I find out that each of my units is 35. I could certainly find the cost of 1 coat and 1 sweater, and then find 3 coats and 5 sweaters. Another way to do this, it's a nice quick way, is to realize that 3 coats is going to have 9 blocks, and 5 sweaters is going to have 5 blocks. Altogether, I have a total of 14 blocks, and I know that each block is 35. So, if I have that, then I can say, well, again, let's try mental anytime. 10 35s is 350. 4 35s, 2 35s is 70, so 4 35s is 140. Altogether, that's going to give me $490 for the cost. By the way, when I'm doing that mental math, again, I'm doing the same thing here. We have 300 and, look at me, I put it over there funny. Put it over too far. Write it correctly and it'll make more sense. It's the same thing as doing 4 times 5 and 4 times 3. That's 140 plus 350. Again, I think it makes more sense to us if we say 10 35s and 4 35s. That's what we mean by 14 35s. And if we can do that and teach ourselves to stretch that way, it's a great way to learn to think about numbers. So the final answer, though, is 490, and I think it's a quicker problem to take it all down to how many individual unit blocks do I have and multiply that by 35. It can be done several ways, of course. Number 5, Jack's monthly salary is $1,850. He gives his wife half of his monthly salary, so that's $925. He spends $348 on himself, and he saves the rest. And he saves the same amount each month. How much will he save in a year? Give your answer to the nearest thousands. All right, so basically what we want to do is find this number and multiply it times 12. So how do you find that number? Lots of ways, right? You could add these two together and subtract it from 1825. I could realize that if this is half, these are equal halves, so this part is 925, and I could do 925 minus 348. To do that, personally, I would think, I wouldn't even necessarily write it down, I need 52 to get up to 400, and then I need 525 to get up to 925, so that gives me a total of 577 in this box. And then I have to do 577 times 12, which I would like to do 5,770, that's 10 577s, plus 2 577s, and when I combine those, I get 6,924. But wait, in the end, always make sure you're reading the question. It asks you to give your answer to the nearest $1,000. So I'm going to round the 6 by looking at the 9, and that tells me that I am going to round it and say, round numbers, if I round it off, he's going to save $7,000 in a year. Number 6. I find that I use a chart like this pretty frequently on a problem like this. It tells us Jamal caught 8 more grasshoppers than spiders, so that's where I came up with this graph, just to keep in mind my numbers. And a grasshopper has 6 legs, a spider has 8 legs, and he has a total of 188 legs. We're trying to find out how many grasshoppers and how many spiders did he catch. And so this graph helps me to solve that in this way. This is my number of spiders and my number of grasshoppers on the opposite ends. In the middle I have the number of spider legs and grasshopper legs, and in the middle I have the very center, I have the total, which I know is supposed to be 188. So this is one way. There's a lot of ways you could do it. This is one way that I do to organize my data so I can figure out what I'm doing. I have no idea where to start. If there's 188 legs and there's 6 legs on a spider, no, sorry, of course not, 8 legs on a spider and 6 legs on a grasshopper. If I put them together, that's 14. That's about, I'm going to have about 10 sets of 14. So maybe I would just start with 10 spiders. You just have to start somewhere. 10 spiders and 18 grasshoppers. I was thinking 10 sets of them. Anyway, whatever. So my chart would be this way: 10 spiders, times 8 legs is 80 spider legs. 18 grasshoppers times 6 legs is 60 and 48, right? 10 sixes and 8 sixes, that's 108. And look what I did. I actually ended up guessing the right one the first time. How about that? If I hadn't, of course, then I would just adjust. If I have, let's look what happens. What if I had 5 spiders and 13 grasshoppers? And by the way, notice that when I pick one to start with, I pick with spiders, and that grasshoppers have to be 8 more than that. Let's say I started with 5. Let's just keep playing with it for just a minute. 5 times 8 is 40. 6 times 13 is 78. And altogether, I have 118 legs. That's not enough legs. And in this case, they're both just going to go up. And I would just go up until I get to the 188 legs. And make that work. Okay, that'll do it. Problem number 7. A shopkeeper had 1,080 apples and oranges altogether. After selling 60 oranges, the number of apples he had was 3 times the number of oranges left. So in the end, the apples were 3 times more than the oranges. That happened after he sold off 60 of the oranges. Now I should do this. In the beginning, before he had 1,080, and then he sold off the 60. So I'm color coding a little bit. The 60 is included in the 1,080. But if I subtract the 60, then I get 1,020, and that's what the blue numbers are. Okay. He had 1,080 to start with. When the 60 went away, I have 4 equal groups. So if I take the 1,020 and I divide it into 4 equal groups, I'm going to have 255 for each of my groups. 1,000 divided by 4 is 250. 20 divided by 4 is 5. So 255 is a pretty quick and easy number to come up with there. What's the question we're trying to answer? How many oranges did he have at first? At first, he had the 255 that we've decided is this box, and he had 60 more than that, so we had a total of 355 oranges at first. Organizing the information to keep up with what you have and how the story goes, and it becomes a simple problem. Problem number 8. Dominic has twice as many peanuts as Leo. Probably by now you're getting really used to drawing boxes to represent numbers so you can figure out what you're doing. How many peanuts must Dominic give Leo so that they each have 288 peanuts? Well, the answer is, of course, he'd have to give him half of a box. But how do we know how many that is? Okay. Logically speaking, if when this happens, they each have 288, there's a couple of ways you could do that. All right. I could take that 288. Notice if these two boxes are the same, this is a half and that's a half, I could divide each of these into halves as well. So if after this box is given to Leo, then I have 288 is how much each of them have. If I divide that into 3 groups, that gives me 96 in a group, and 96 is the amount of peanuts that Leo has to get from Dominic in order to have the same amount. That is the short, I'll say lovely mathematical way to do it. You could also say if they're each going to have 288, then the full amount of peanuts that they have is 576. And if originally those 576 were 3 groups, then each of those groups is 192. And if they're all going to have 288 in the end, Leo started with 192. If he's going to have 288, then he must have received 96 peanuts. It works the same. Of course, there's a lot more math on this side. By drawing the picture, you can see it pretty quickly, especially if you go ahead and draw the picture. What does it look like when they all have the same amount? If he starts with 2 boxes and he starts with 1, for them to have the same amount, half the box has to be given away. And that's the key to doing it the short way. Otherwise, nothing wrong with this way. It's a happy solution, gives you the right answer. Number 9, Dahlia pays $216 for 4 blouses and 5 skirts. A skirt costs 4 times more than a blouse. How much did she pay for the 5 skirts? Again, remember, we could figure out, well, I think the easiest way to do this is to say that 4 blouses are 4 squares. And if you're going to buy 5 skirts, then you're going to pay 20 squares. And so the total amount that you pay is 24 squares, and we know that that's equal to $216. So, do you know what's next? 216 divided by 24, that would be 9. And so each of my squares is 24. The question is, how much did she pay for 5 skirts? 20 times 9 is $180. Again, please get in the habit of stating your answer. 5 skirts cost $180. Nice and boxed in, so it's easy to find, is a great skill and habit to get into for a math student. Now you could go back and find the individual cost of a blouse and a skirt and write it all down. A blouse is $9, a skirt is $36, and you could do 36 times 5 to get the same answer. But why would you, right? If each square is $9 and 5 skirts cost 20 squares, you can do it the easy way. Number 10. Tim and Shelley have a total of 3,450 coins in their piggy bank. And Shelley and Nina have 5,130. Here's what we need to know first. Nina has 5 times as many coins as Tim. All right, paused and drew a little bit for you. I made Shelley's coins a circle. I don't know if it's a big box or a small box. I just made it a circle, so we realize that she has some, but we have no idea how it compares to Tom's and Nina's. But I do know that if I combine Tim and Shelley, I have 3,450. If I combine Shelley and Nina, then I have 5,130. Does it strike you? At some point, we want it to be intuitive to say, oh, I see what this is. Here's what we want to realize. A square in a circle is 3,450. 5 squares in a circle is 5,130. The difference between these two, between 3,450 and 5,130, that difference is 1,680. And the thing that's different about these two numbers is these 4 squares. So because Shelley, although I don't know Shelley's, because Shelley's is the same in both groups, and one group has one box and the other group has 5 boxes, the difference is the 4 boxes that are there. That tells me that the difference of 420 per box. Each of those boxes is going to be 420. So the question is, how many coins does Shelley have? Well, the easiest way to do it from there, if this is 420 and Shelley has the rest, I'm just going to subtract 420 and find out that Shelley has 3,030 coins. Now, I would always suggest that students check their work. If Shelley and Nina have 5,130 and I'm saying that Shelley has 3,030, then that means that Nina has 2,100. If she has 5 boxes and every box has 420, then sure enough, that comes out to be 2,100 coins. And so that checks out and says that everything it told me is correct, and I can make my final statement, because the question is, how many coins does Shelley have? Shelley has 3,030 coins. Number 11. Nicholas collects 3 times as many coins as William. Yasmin collects 21 coins less than Nicholas. Now, I have no idea if that's 1 box or 2 boxes, if it's almost the same size. All I know is Yasmin is 21 less than Nicholas. And what I'm told is that the 3 children collect a total of 427 coins. And by the way, make sure we're aware of the fact that these 21 don't exist. The 21 are not in the 427, right? The 427 is that box, which is an unknown size, and these 4 boxes. So the question is going to be, how many coins does Yasmin have? I want to pause and see. I hope that as we go through, things begin to click. In order to make this something I can talk about, what I would need to do is add the 21 to the total, only if Yasmin had 21 more. Then I would know that I had 3 and 3 and 1 equal parts for the 3 people, the 3 children, coin collectors. So 448 would be how many I would have if I had 7 equal parts. If I take 448 and divide it by 7, and get 64, then that would tell me how many each box is. So then go back to the question. I'm being asked how much Yasmin has. Yasmin doesn't have 3 boxes like Nicholas does. She has 21 less than that. So she has 192 minus 21, or 171 coins belong to Yasmin. Number 12, Katie is 16 years younger than Tess. Nina is 8 years older than Katie. We're just going to, again, represent it. The sum of their ages is 189. Find the age of each. We're kind of comparing everybody off of Katie. Katie is 16 years younger than Tina. And again, it's always easier to add than subtract. So if somebody's 16 years older, I would generally speaking, add 16 rather than subtract 16. Add 16 to Tess instead of subtracting 16 from Katie. Nina is 8 years older than Katie, so it looks kind of like that. And the sum of their ages is 189. To find the age of each, in this case, to get my 3 boxes by themselves, I need to subtract the 24. If I have the 165 and divide that by 3, that will give me my equal boxes. So if each of my boxes is 55, the question is to find the age of each lady. So then Nina is 63, Katie is 55, we should probably say years old. They're not 55 days or 55 decades. Katie's 55 years old, and Tess would be 71 years old. Number 13. Andy and Barry saved a total of $368. Cindy and Daisy, a total of $246. Andy and Daisy have the same amount, and Barry saved 5 times as much as Cindy. Lots of information. Here's how I chose to represent it. Again, Andy and Daisy have the same amount, but we don't know anything about that compared to the other people. I do know that Barry has 5 times the amount of Cindy. And I know that together these two have 368, and these two have 246. And we're trying to find out how much each one had. Very frequently, the earlier problems build up to be a similar skill or kind of combined skills to do the harder problems at the end. This is really similar to a problem we just had worked in that we realize that the difference between these two is the fact that this one has 4 squares. So 368 and 246 have a difference of 122. If I divide that by 4, what we end up with is $30.50. Now, in this case, since it's money, I can have decimals. I can't have half of a marble, right? But I can have $30.50. And so that's going to be our starting place, is that each of these squares is $30.50. So we can certainly start and already say that Cindy has $30.50. And Barry has 5 times that amount. That would be $150 and $2.50, so $152.50. Now, Andy and Daisy are going to take a little bit more math still. Not too bad, though. I know that Cindy has $30.50, and so Daisy, if I subtract these, is going to have $215.50, and I'm told that Daisy and Andy have the same amount. I would suggest that you not have your student leave this problem until they've checked their work. These kinds of problems are so easy to check, and I can't tell you how many times I find that I make a mistake. What we want to do is check and see, basically if I add Cindy and Daisy, I'm supposed to get 246. And I can see pretty quickly and easily that I do in fact get the right number. If I add Barry and Andy, I'm supposed to get 368. And it doesn't take much glancing to see that that does work and that I have the right answers. But take that little extra time to look at it. So many times I think I've done it right, and then I look back and I realize that something is a little bit off. Problem number 14. We have a musical where an adult ticket is $54 and a child ticket is $36. And there are 30 more adult tickets than child tickets sold at the end of the day. And they collected $9,000 for the event. How many adults and children attended the musical? All right. One thing we can do, this actually turns out to be a simple problem, but it's leading up to a kind of problem that is going to be a little more involved, but we'll start with this type. If there's 30 more adult tickets sold, then $54 per ticket times 30 tickets is going to be $1,620. So if I take the amount collected and I subtract the amount of those extra adult tickets, then I come up with $7,380. Now, maybe I should draw a picture here and do this. I think this is the best way to maybe give a graphical understanding of how I'm setting this up. The tickets are sold to adults and children, and they would all match up, except at the end of all the children tickets, there are 30 more adult tickets sold. Before that, every adult and child had the same amount of tickets, but when you match them all up, you run out of children's tickets, and there's 30 more adult tickets sold. If all of these cost $9,000, I know that these tickets cost $1,620 for the 30 adult tickets, then the tickets that I sold up here are $7,380, because again, they combine to be $9,000. But the tickets up here are all paired up. If I bought a pair of adult tickets and child tickets, I would pay $90. So if I take this $7,380 and I divide it into $90, divide it by 90, then that will tell me how many pairs of tickets I bought or were purchased. I didn't buy them, somebody bought them. And if you do 7,380 divided by 90, you get 82. 82 is the amount of pairs. 1 pair, 2 pairs, all the way down to 82 pairs of tickets. Now that might take a little bit of thinking. When you've done Singapore math for a long time, that kind of thinking becomes very quick and easy, but I want to make sure that I don't assume that you already have thought through and understand how to do that. All of the tickets, the adult tickets and the children tickets, can be paired up until I run out of children's tickets, and then I have the 30 tickets left. The $9,000 for the total is made up of the extra adult tickets plus the paired tickets. When I pair a ticket, if I buy a pair, an adult and a child, I pay $90 a piece. So that tells me I have 82 pairs. The question is, how many adults and how many children attended the musical? The child tickets sold were 82. The adult tickets were 82 plus the additional 30 for 112 tickets. There were 82 tickets sold to children and 112 tickets sold to adults. Number 15 needs a chart. I'm told that there are 30 bottles of olive oil that sell for a total of $264. I have some that are small that sell for $8 each, and I have some that are large that sell for $12 each. That's a times $8 times $12, and a total of 30 bottles. So if I want to figure this out, first thing I know is my number of small and large bottles has to add up to 30. So I could try with 15 and 15 and just see, if it was right in the middle, where would it be? 15 times 8, I'm going to see how much would I pay. If I got 15 small bottles, 15 times 8, that's 80 and 40. that's 120. 15 times 12, that's 150 and 30, so that's 180. That total would be $300. If I spend $300, I'm spending too much. I want to spend less. How do I spend less? Well, I need fewer big bottles and I need more smaller bottles, because remember, my total is going to add up to 30 bottles. So if I need the total amount to go down, I need to buy less expensive things and more cheaper things. So if I go down to 20, I have 20 times 8 is 160, and 10 times 12 is 120, and that gives me 280. That was good. I went in the right direction. I'm closer, but I'm not there yet. Now, you can also make some extrapolations. You can look at this and say, you know, when I did this, I went down $20. I need to go down not quite another $20. So if I go down, probably if I go to 25 and 5, it's going to be a good guess, but that's probably a little too far. I would expect that to be $260. So if I don't want to be quite that far, if that's going a little bit too much, then I think I'm going to try 24 and 6. Now, you can try as many of these as you want to, right? You can fill up the whole chart. If you want to guess smartly, then you can notice things like that. If you just want to guess and check your way to the answer, that works. But if I buy 6 large bottles at $12 a piece, I pay $72. If I buy 24 small bottles at 8 a piece, it's $160, and 32 makes $192. And when I add these together, joy of joys, I get $264. So the question is, how many small bottles were sold? If there were more small bottles than big bottles sold. I didn't even read that part, but we know there's more small bottles than big bottles. I guess we could have started with another number. I knew going in, if I'd read the question carefully, I would have known going in it wouldn't be 15-15. I could have started with 20 and 10 and saved one whole step. But what I know in the end is that there are 24 small bottles and there are 6 large bottles that are sold. You know, the reason they said that is because I could have actually, let me set it up for you. I was thinking maybe I could do it all with big bottles, and I actually can't. If I used 22 large bottles, I would spend the right amount, but I wouldn't have 30 bottles, which is the requirement. So interesting that they put that in there. There's really only one answer. All right, so then we're going to continue on and talk about the challenging problems. This particular group of challenging problems I do find quite challenging, at least some of them. And to some extent, it's a skill you either have or you don't have. And to be completely honest, I don't really have the skill all the way myself. The only thing you can do with some of these is for number one especially is one of them, is just kind of play around with it and see if it occurs to you. And I do think it's a good thing to look at it, mess with it, play with it for a while. And when your child is tired of messing with it and playing with it for a while, look at the answer and say, oh, that's what I could have done. So really all I can do to help you know how to do this is basically show you the answer and see how we could have done it, or see how you could see it. One thing you're doing is trying to get to 1,000 by adding up a number, and you're allowed to have 8, the digit 8 times. So at some point it has to occur to you that you have to use 888, and maybe you do 1,000 minus 888 and realize that you need more than that. Maybe at some point you realize to get a 0 on the end, if it's supposed to equal 1,000, then you would have to have 5 8s at the end. You know that there's 5 numbers, and 5 8s is going to give you a 0. You have to have an 8 over here that you can add a 2 with to get you there. And that 16 and 4 is going to give you 20, and that works out. That's one they may be able to come up with by playing around with it a little bit. Number 2, the pattern that they're doing is they have the numbers in the circles and the number in the triangle, and in the, we'll call that an upside down smiley face, there's another number. And what you find is if you multiply the 3 times 4 and you subtract the 5, it equals 7. 12 minus 5 is 7. In the second problem, it's 6 times 4, subtract 9 equals 15, because 24 minus 9 is 15. So the last problem, they want you to find 7 times 5, subtract 11, and you would get 24, because 35 minus 11 is 24. You can look at it, you can play with it, maybe you see it, maybe you never see it, but trying a lot of possibilities, thinking through, am I adding, subtracting, multiplying, dividing? You can assume that you're going to use all of the numbers. The pattern has to be the same from one mask to the next, and you've got to find how to do that. On part 3, sometimes we make assumptions that aren't true. I got A pretty quickly. I didn't get B till I looked in the back of the book, and then I kicked myself because I made an assumption that was not true, and it messed me up. So if I want to use 6 nines to get a value of 100, 9 times 9 is 81. That's pretty close. I know that 9 times 11 would give me 99. If I get 81 and I add 2 more 9s, that's 11 nines, but I'm only at 99, and what you have to do is realize that you can add 1 by adding 9 over 9. And so that uses 6 nines, and it basically is 11 nines plus 1. And for whatever reason, that jumped up at me pretty quickly, and I saw that. On the next one, what I didn't think of was doing it similar to number 1. If I have 6 sevens, they started with the number 777. I was trying to use individual sevens, and it did not work. But if I take 777 and I divide by 7, and then I subtract 1 in the form of 7 over 7, then I have, of course, 111 minus 1 is 110, and I used 6 sevens to get there. I made an assumption that I was trying to use single digits and multiply or subtract or add, and it just wasn't working. But by spending the time on it and then finding the answer, it causes me to feel the pain of the assumptions. And so maybe next time when I'm working a problem and it's not working, I might stop and think, what assumptions am I making that might be causing this not to work, and that I could get it correct if I didn't do that. Number 4. These problems make me sad. They are hard for me to do. Sometimes I can find a limiting factor that solves it. To be honest, I didn't find any of these to be simple. I'll let you look in the back of the book. Maybe someday I'll find the trick to this and be able to teach it. But really, it's so much of a guess and check that I don't even have anything good to tell you. It's a great thing to come up with an organized way of checking options. And if your child enjoys word puzzles and all of that, great. The answers, again, are in the back. They don't really give any hints in the back on how to solve it. They just tell you, sure enough, there's a set of numbers that makes all of those work. And I spent a decent amount of time on it trying to find a way to teach it, and I just didn't see anything good. So maybe as I teach Singapore Math Live for a while, I'll get smarter. Right now, I'm just going to say, if you've got a child who figures out how to do it and you want to call me and teach me how, I would be happy to learn from you and your child. Number 5. If you write down all the digits from 1 to 100, how many times do you write the digit 3? We see this problem many times in Singapore Math. Eventually, you begin to learn the pattern, right? In the ones place, You could write the 3 as a 3 or a 13 or 23 all the way up to a 93, and that tells me that there are 10 digits of 3 in the ones place. In the tens place, there's 30, 31, 32, 33. Now we've counted this 3, but we have not counted this 3 yet. Okay, so that one's already counted. We don't have to worry about that. 34 all the way to 39. And again, there are 10 3s in the tens place. So altogether, the digit 3 occurs 20 times. Number 6, another very common math problem that teaches you about assumptions. Let me draw a chart for us. As with many times in numbers, you're looking for a pattern. Notice that how I'm going to organize my data is to say I have a day, like for example on day 1, I start at position 0 at the bottom of the jar, and I end at position 3 centimeters, but then I slide back down to 1 centimeter. So on day 2, my starting point is at 1 centimeter, I end the day at 4, and I slide down 2 to a position of 2. Let me do one more. At day 3, my starting point is where I slid to, right? So I start at 2, I go up to 5, and I slide back down to 3. So the tricky thing here is somebody says, well, on each day I end, my end of the whole thing is at 1, at 2, at 3. The day 1 I end at 1, day 2 I end at 2. And so somebody says, oh, on day 30, I'm good. He gets out of the jar. Day 30 is out day. Hold on 1 second. Okay, so on day 30 he would get out. That's the first answer that is really not thought through enough. It's kind of an intuitive, quick answer. What we have to realize, do you see it yet? What happens is when he gets to 30 in this column, he's out. He doesn't have to wait until he slides down. He doesn't have to go to the lip of the jar, slide down, and wait till he can climb out at the end of the day. As soon as this one gets to 30, he can get there. So what is the relationship between these two numbers? The end is always 2 more than the day. So this would be on day 18. I'm sorry, 2 more, that'd be 28. On day 28, they always start, notice the pattern's always the same. You start 1 less, you end at 30. Now he would slide back down to 28, except when you get to 30, he's going to climb out. So the correct answer is he climbs out on day 30. I'm sorry, on day 28. Some sort of an organized chart that finds the patterns is going to be the way to solve that.